Hi, I am Gazi Hasnat, a master's student at the University of Saskatchewan. In this video, I will present my work on control line stylization to visualize multivariate information supervised by Debajyoti Mondal and Gutwin. Contour map is a popular way to visualize one variable's distribution using control lines and contour bands. It also shows certain value increase or decrease using visual cues like color. Now that's one variable. In a situation where there are multiple variables, the challenge is to visualize all in a single view. The popular alternative of using glyphs suffers from visual clutter and base map overlap, whereas a grid view lacks geospatial connectedness and gradient information. Therefore, our goal was to see if the base control lines, which are already present in the map, can be leveraged to visualize the other attributes. To do that, we created 5 designs to visualize 4 variables. Let's take a look. The first design is called parallel lines, where the contour lines of A are used to visualize B, C, and D in 3 parallel lines. The thicknesses of B, C, or D at a specific point is mapped from their corresponding values. In color blending, the thickness of the line depends on D, and the color at that point is a multiplication blend of B and C color shades, from white to red and white to blue, respectively. In pi, each of the 3 variables have 120-degree space allocated in each circle that they fill according to their values. The fourth design is thickness and shed, where B and D control the thicknesses of the blue and red lines respectively, and C controls the shades of blue. Finally, side by side shows B, C, and D separately, where the values control the color shades. Now, 2 most important parameters of a contour map are contour line width and the number of contour intervals. So we conducted our first 2 studies to investigate the effects of these 2 on visual interpretability. With the observation of those 2 studies, we conducted our final study, where each task was completed on both real-life datasets and synthetic datasets. The results reveal that real-life dataset has more accuracy than synthetic data, which is because real-life data has simpler spatial correlations. And design-wise, parallel lines and side-by-side have more accuracy than color blending and thickness and shed, where pi is a reasonable compromise between 2 groups. Interestingly, design performance also varies from task to task, making one design better than the other in one task, but the opposite in another. Let's see an example where we need to select the contour part with the maximum difference between B and C. In color blending, the solution is to select the contour part with the most red or blue in it. As we can see, the regions 2 and 3 have lighter shades than 1 and 4, so they're eliminated. Now, between 1 and 4, it's a bit hard to choose one because both are reddish. And moreover, as you can see from the diagonally placed boxes in the legend, a darker shade can mean equal or similar amount of B and C. Now, if we go to parallel lines, it's much easier to say that one is the right answer, as we can clearly see the actual values of B and C separately, making an easier difference calculation. Therefore, parallel line is the winner. Now, in the second example, we need to select the contour part with the maximum change in B values. In parallel lines, the question wants us to only consider the red lines and pick the one with the most changes in thickness. Well, we can easily eliminate 1 and 2 because they have constant thicknesses, but between 3 and 4, it might take more time for an user to detect the right answer. Now, if we go to color blending, it's easier to detect 4 as the right answer because it clearly shows more changes than 3. Therefore, color blending wins here. So finally, we generated a table that recommends designs to use for various task domains in 3 different environments. Each of our 5 designs was recommended in at least one scenario. Let's see a real-life application now. The left picture shows some red and blue lines known as fronts, which are detected by the National Oceanic and Atmospheric Administration using softwares or by painstaking inspection of the numbers plotted on the map. We try to visualize this using our parallel lines design, which readily reveals some of the interesting curves that match some of the detected fronts. This shows the potential of using control line stylization alongside our traditional ways. Lastly, the final takeaway of the presentation is contour lines that are already present in a visualization can be leveraged to effectively convey information about other geospatial variables. Thank you so much for your hearing. Thank you all.